If there's one thing that distinguishes Solana from most other blockchains, it's how the protocol solves one of the most fundamental problems in distributed systems: time. In a decentralized system, there's no shared clock everyone implicitly trusts. Yet, agreeing on the order of transactions, what happened first, second, and so on, is critical for correctness. How Solana approaches this problem is central to its performance. Today, we'll talk about two parts of Solana's consensus: proof of history and Tower BFT, as well as the Alpenglow upgrade, a major upcoming evolution in how Solana reaches agreement on the network. Most blockchains don't have a native notion of time. Instead, nodes must communicate repeatedly to agree on ordering. In Bitcoin, this happens through proof of work and longest chain rules. In many proof-of-stake systems, nodes must repeatedly exchange messages to converge. Both approaches work, but they're coordination-heavy and slow. The more time nodes spend just agreeing on order, the fewer resources they have for execution, and the longer users wait for finality. Solana's approach reduces that coordination overhead by encoding time directly into the ledger. Proof of history is not a consensus mechanism by itself. Instead, it's best understood as a kind of verifiable delay function, VDF, a cryptographic function that takes a prescribed amount of time to compute but is fast to verify. Under the hood, POH is implemented as a continuous, sequential hash, essentially a chain of SHA-256 outputs where each output depends on the previous one. Because this process cannot be parallelized, it naturally encodes the passage of time. When transactions are submitted, they're stamped with positions in this hash sequence. Anyone can then verify that one event occurred before another simply by checking the order in that hash sequence. This makes POH a kind of crypto clock, a verifiable timeline that every node on the network can reference without constant back and forth communication. The outcome is a significant reduction in messaging overhead and a shared source of time that every validator can trust. Proof of history alone doesn't give you consensus. You need agreement on which block to accept and when it's final. That's where Tower BFT comes in. Tower BFT is Solana's implementation of practical Byzantine fault tolerance, PBFT, optimized to take advantage of the time ordering provided by POH. In traditional PBFT, validators send many rounds of messages to ensure they have agreement before finality. In Solana's Tower BFT, since all validators already share a verifiable clock via POH, they can make voting decisions with far fewer on-chain messages. Validators vote on blocks and then lock in those votes progressively. As more votes arrive, it becomes exponentially harder to undo those decisions. What this means in practice is much faster finality. Solana doesn't need to wait minutes to be confident a block won't be reversed. Validators can use the timeline in POH to quickly converge and finalize transactions. Proof of history and the Tower BFT together are why Solana feels fast in practice. Transactions are ordered and finalized with minimal coordination overhead. Because validators don't need to endlessly exchange messages, they can focus on execution and replication. Blocks move forward quickly, clients see confirmations rapidly, and applications can build real-time user experiences without long wait times. In many blockchains, users accept multi-second or even multi-minute delays as part of using the network. Solana was designed so builders don't have to, without sacrificing safety in the process. At BrickPoint 2025 in Abu Dhabi, the Solana ecosystem unveiled one of the most significant protocol upgrades in the network's history: Alpenglow. This upgrade is not a tweak. It's a fundamental rethinking of Solana's consensus architecture. Alpenglow replaces key parts of Solana's current consensus stack, including proof of history and Tower BFT, with a new consensus protocol designed for even faster finality and simpler coordination. Instead of POH serving as the global clock and Tower BFT performing voting, Alpenglow introduces two new components. First is Vaulter, a streamlined voting and block finalization mechanism that can finalize a block in a single round of voting if enough validators participate, or in a second round when needed. Then there's Router, a redesigned data dissemination protocol that replaces multi-hop turbine with a single-layer relay system, reducing propagation delays and improving resilience. Together, Vaulter and Router dramatically simplify how blocks propagate and become final. Simulations and research indicate that Alpenglow could reduce Solana's transaction finality time from the existing 12 seconds down to around 100 to 150 milliseconds, a nearly 100x improvement. This level of responsiveness isn't just a performance headline. It pushes Solana's consensus into territory comparable with high-performance Web2 systems. For developers, this means confidently designing experiences where users virtually never wait for a confirmation, even on a global, decentralized network. Alpenglow is also designed to maintain strong real-world safety. It incorporates a 20+20 resilience model that tolerates meaningful levels of both adversarial activity and non-responsive validators without degrading liveness or safety. In terms of timeline, Alpenglow passed validator governance with overwhelming support in September 2025, with roughly 99% approval, clearing the way for implementation. Solana's approach to time and consensus is one of the core reasons the network can support the rich ecosystem we talked about in the last session. Proof of history gives the network a verifiable timeline. Tower BFT lets validators agree quickly and safely. And Alpenglow represents the next evolution, a simplified, dramatically faster consensus design that pulls finality into the realm of real-time responsiveness. Understanding how Solana solves the time problem explains not just why it's fast today, but how it's evolving to stay fast tomorrow. In the next session, we'll shift from time to scale and talk about how Solana is designed to process many transactions in parallel.